Hello, everyone. My name is Omar Elsewedy, and today, alongside my colleagues, Mustafa, Yasmina, Ali, will be presenting our thesis project. So this is a simple table of content for today's presentation. We'll first start off with talking about the problem, and then we'll discuss the data sets, the methodology that we have followed, and then we will do some analysis of the results that we have gathered. So let's first start from the beginning. What is an asset, the portfolio asset management? So asset management is the process of allocating capital to a set of assets, and it involves two key aspects, the tactical asset allocation and the strategic asset allocation. We're working with the tactical asset allocation. So what is TAA, or the tactical asset allocation? It's dynamically adjusting weights within a portfolio to achieve a specific financial objective, and it aims at capturing market trends in the short and the medium term. And the major challenge with the problem is relies in the estimation errors of the forecasted expected return of a given portfolio. Now, my colleague Yasmina will tell us more about the related work.
So there are multiple approaches to how to solve a tactical asset allocation problem, and we'll talk about a few of them. So the first of which is presenting the tactical asset allocation problem as a Markov decision process, which can be solved using dynamic programming. The second approach is using deep neural networks with macroeconomic data in conjunction with price value data in a forward step setting to solve the tactical asset allocation problem. The third approach is the critical line approach algorithm, and it's developed by Markowitz, and it's a very remarkable algorithm. However, it suffers from some downsides, some of which are that small changes in the return predictions can lead to significant changes in the portfolio allocations, and it relies on the inversion of the covariance matrix, which is a high-cost operation process. And another downside is that while diversification is important, correlated investments can suffer from estimation errors. So to reduce the dimensionality of the problem, we made some assumptions, the first of which was that the market is tradable and liquid at any point of time. There's no short selling and there's no transaction costs. And we used Python and some libraries like stable baseline and OpenAI. And now my colleague Mustafa will tell us more about the datasets.
So throughout the project, we used two main data sets. The first one was the current cryptocurrency data set. It consisted of around 122 cryptocurrencies and tokens, and it ranged from January 2021 to December 2022. We gathered it from Binance.com, and after the data manipulation, it came around to 1,600 rows of data of hourly close prices of each cryptocurrency. The second data set was the Dow Jones 30 Industrial Average. It consisted of 30 stocks, and it ranged from February 2009 to December 2020. We gathered it from Yahoo Finance, and after the data manipulation, it came around to 3,000 data rows. And initially, it consisted of the daily high, low opening and closing, plus the volume traded. And we can see two examples of each data set down below. The left one is the cryptocurrency one, and the right is the Dow Jones. Quick thing to mention, we used the cryptocurrency one for the hierarchical clustering part of the project, and we used the Dow Jones Industrial Average for the deep learning aspect. Now my colleague Ali will explain to you the hierarchical clustering.
Before we can dive deep into the methodologies, we need to talk about a vital concept, or rather multiple vital concepts, but the first of which is hierarchical clustering. So Hierarchical clustering can be used for challenging the tactical allocation problem that we defined earlier. And we use two specific versions of hierarchical clustering. I'm not going with mics, I'm sorry. I'm not going with microphones. The two hierarchical clustering methods we used are HRP, hierarchical risk parity, and hierarchical equal risk hierarchical equal risk contribution, aka HERC. So the way they work, the way both of them work, that is that firstly, you input a covariance matrix. Then after inputting the covariance matrix, you then perform hierarchical tree clustering. Once you get the tree clusters, you then perform matrix seriation so that the data can be evenly spread in a readable way. Afterwards, you then perform, as the dendrogram portrays, a recursive bisection. The difference between the two methods, right, as seen here, which shows HERC, is the fact that HERC, despite performing the same thing, does two things differently. The first is that it performs it generates an optimal amount of clusters before performing the bisection or even the matrix seriation. It also performs naive risk parity, and as you see here, each and every single one of the bits of data are shown by the risk. Like they're divided by the naive risk parity. Now my colleague Mustafa is going to talk about Gerber statistic.
Thank you, Ali. Now, as we mentioned before, the hierarchical clustering requires a covariance matrix to compute. We decided that throughout our research, we found a Gerber matrix is more robust and insensitive noise to compare to the covariance matrix. It gained, we found a paper published on it in 2021, and it showed that if we set a data-dependent threshold, it excludes the outliers and the noise. However, it is prone to one limitation. It does suffer from confusion zones. And as we can see here in the graph, the Gerber matrix shows the correlation between two assets. The more correlated they are, the lighter the color, and the less correlated, the darker. We can see that along the diagonal, it's very bright because that's the correlation between the asset itself to itself. And it clusters the lighter assets, the more correlated assets together, and thus producing this Gerber matrix. Next slide.
So as Yasmina was telling us that the DRL, the deep reinforcement learning, is one of the approaches to approach the tactical asset problem. So we've tested this approach and we followed a certain methodology and we developed 4 reinforcement learning algorithms and we tested them. We'll discuss the results in a few minutes. So the methodology that we followed for the DRL, we first used the Dow Jones data set we propose an autoencoder to perform stock selection, and then we add some technical indicator feature engineering to the stocks, and then we do data split in an 80-20% fashion for the training and the testing of the model. And then we build a benchmark portfolio, 2 benchmarks portfolio, the equal weight portfolio and the mean variance portfolio to benchmark against the 4 models. And then we did some back testing and evaluation of these models against the benchmark. So we'll talk about more about these methodologies. So first, we propose an autoencoder when we have 30 stocks in our input layer with a decoder of a dimension 5, and an encoder, of a dimension 5 and a decoder of a dimension 30 that reconstructs the stocks, and then we select the 20 least recreation errors, these stocks, to continue to build the basic portfolio. And then we add 10 technical indicators to each stack or each stock in the data set. And to reduce the dimensionality of the problem, we propose an unsupervised stack restricted autoencoder. It is employed to reduce the technical indicators from 10 to 4 for each stock. To get an idea of about the technical indicators, these are just to help the model of get more features about understanding the performance of the stocks within the market. And then, as I said, we split the data set in a 20 and 80% fashion. So the training data set span from 2009 to 2018, and the testing is around 2 years from 2018 till the end of 2020. And then, as I said, we constructed two benchmark portfolio, the equal weight portfolio and the mean variance portfolio. And these are the simple diagram of the weight distribution of the both portfolios. And here are the deep reinforcement learning models. So to understand this better, we model the tactical asset allocation as a Markov decision process. And we use the deep reinforcement learning to solve the Markov decision process. So get a better idea of how this works in practice. So we developed a Markov decision process, as you can see, and it consists of 4 main aspects or components for the machine learning environment. So we have first the state, which is the input that gets fed to the model out of the environment. And in our configuration, it's the high and the low and the close and the covariance metrics and the technical indicators that we talked about that gets fed to the model. And then the model tries to optimize a policy that determines them to take an action that maximizes the reward function. And in our case, the reward function for the model is the total portfolio value. And now the model takes an action based on the state and the reward that he gets in the previous step to improve and take it for the next step. So the action that the model takes is a weight vector that rebalances the weights of all the stocks data on a daily basis. So as you can see here, the environment consists of the stock prices and the balance data. And these are the 4 reinforcement learning models that we have developed and tested. First is the actor critique model, and then the proximal policy optimization, the deep deterministic policy gradients, and the twin delayed DDBG. Now, my colleague Mostafa will tell us more about the results we gathered from the hierarchical cluster.
As we can see here, we can see the 2 hierarchical clustering algorithms combined with the Gerber statistic. On the left is the HRP one. Let me further explain how the process goes. First, the benchmark that we used on how the algorithm performs is by giving it a budget, a certain budget. In our case, it was 1,000, and we gave it a certain number of steps. Here, as we mentioned before, the cryptocurrency dataset is an hourly dataset, which means every step is correlated to corresponded to 1 hour. Now we gave the clustering algorithm various types of steps between 20, 40, 50, 80, and 100, and it reallocates the weights every step after every increment of the step. This is because we wanted to capture certain trends or movements in the graph and make it reflect in the portfolio later on. So in HRP, one last thing, the data set, the cryptocurrency one, in the first 4 months, there was a market boom and then there was a market crash. And this is important because we can see in the HRP graph, it spikes greatly in the first 3,000 hours, and then it crashes tremendously. We chose this data set specifically because we wanted to see how our algorithms perform in such market scenarios. Moving forward to the end, we can see that the best performance was achieved by the HRP in 80-hour steps. And it came around 1,100 something portfolio value in the end, while the HERC performed very well with the 100-hour steps, and it outperformed the HRP. It did achieve better results, the HRP. My colleague Omar will continue.
As my colleague was saying, the HERC, the hierarchical equal risk contribution portfolio, did outperform the HRP. So we benchmarked the HERC Gerber statistic portfolio against the 4 GRL portfolios that we have built. We excluded from the result of the graph that you're seeing now the least 2 performing models, which were the DDBG and the TD3. This is the graph of the cumulative return across the testing split of the data set that span from 2018 till the end of 2020. And as I was saying, the agent interacts with the environment in an exploitation manner, which means he does more of the decisions that he did previously that generated maximizes the reward function and tries to explore more of the decision that could generate greater reward function. So as we can see here in the data set, prior the market crash that happened at the beginning of the 2020, the Max Sharp, most of the DRL portfolios and the herd portfolio did outperform the Max Sharp portfolios with the mean variance optimization, the two benchmark portfolio that we are using to evaluate the performance of our models. And as you can see here, after the market crash, as the rises go, the Max Sharp portfolio at the end of the test did outperform the models, and we can due this to the market crash of the COVID-19 for the data set. This is actually one of the limitations for all these solutions is they are suffer in the certainties of a market crash or high uncertainties in the market. However, this is not the full story. So before I'll show you some statistics for each of the model, I want to explain first two statistics that we are using to evaluate how the models performed in terms of the return and how the model adjusted for the risk, because the cumulative return does not tell the first story. So the Sharpe ratio is basically the expected rate of return of a specific portfolio minus the risk-free return over the standard deviation, which in this case is the volatility of the portfolio. And the max drawdown period is comparing the peak from the lowest period that has a drop in the performance of the model. And it's a risk metric to give us a better understanding of how the losses the model encountered in the testing period. And this is the 4 DRL portfolios benchmarked across the two benchmark portfolio, the equal weight and the mean variance optimization, which is the Max Sharp, and the Dow Jones 30 Index Fund, which are the data set that we are using in the first place. So as you see highlighted here, the cumulative return of the Max Sharp portfolio, as I was saying, did outperform all the DRL portfolios at the end. But as you can see here, the Sharpe ratio for the ATC model, which is the best performance across out of all these models, it achieved a Sharpe ratio of 0.79, which is like 79% in 2 years, compared to the Max Sharp portfolio, which has a percentage of 0.733, which 73%. And if we pay close attention here to the max drawdown, you see like all the DRL portfolios, the 4 of them, had at least max drawdown period compared to the benchmarks, which should tell us more that these models take more into consideration for the risk-adjusted returns across the testing period. So I'll leave you with my friend Ali, who will tell us more about the impairment outcome.
So our project is for purely academic and researchational purposes, specifically within the field of computational finance. The methods themselves contribute, right, by merging hierarchical clustering alongside DRL. It doesn't necessarily beat the Sharpe ratio, or rather in this case, the mean variance, but it does do better in most of the market regimes via the benchmark index. The rebalancing periods usually already need optimization, which is also further reason as to why the research is valuable. And hopefully, as a result of all of our research, we plan on publishing a research paper on the Journal of Financial Management. Thank you.
Please note that this project was under the supervision of Dr. Cherif Salama and Dr. Nouri Sakr. They had to endure a lot to deal with us for the past year. So this is from us to give them like thank you for all your effort and your time, and thank you all for your time.
Thank you.